We're going to talk about something that makes Nyquist very interesting, very powerful, and very useful. And that is this concept that I call behavioral abstraction. What does that mean? What's a behavior? Well, the simplest behavior we can talk about probably is the unit generator OSC or OSC. What does that do? It generates a sinusoid. So that's an example of a behavior. We sort of know what a sinusoid does. It's kind of behavior-like. It changes over time. That's why it's called a behavior. Now, the interesting thing is that it's not just a single value or a single frozen function, because, as you know, a unit generator, the OSC unit generator, can generate sinusoids at different frequencies and different durations, and so that makes it an abstraction, right? It's not a single sinusoid. It just represents sort of all sinusoids of constant amplitude and constant frequency. Now, to be useful, we would like to be able to do things like specify the duration of an oscillator or stretch an oscillator. And so then we have to ask ourselves, what does it mean to stretch an oscillator, or any signal for that matter? If we took the really simplistic view and said, well, an oscillator is just a certain number of cycles from time A to time B, and when we stretch it, we should just linearly transform that and literally stretch it out. That is not so useful, because what a musician wants to do, when you tell a musician to play a note for longer, the musician will insert more oscillations, so hold the pitch and hold the frequency steady, but produce more oscillations to fill up the desired time. Okay, that's a sort of an abstract idea of what that behavior is and what stretching means. And so the big challenge in Nyquist is when we have all of these signals and all of this capability for manipulation, how can we build abstractions that do the right thing when we stretch them, when we transpose them, when we do other operations on them? And not only do we want things to do the right thing, but we want programmers, that means you, have to be able to define your own functions that behave according to whatever you want that function to do. For example, if I want to play a drum roll and I want to stretch the drum roll, what does that mean? It probably means that I play more notes, okay? But if I'm playing a violin tone and I want to stretch the violin tone, I don't play more notes, I just make the note longer. So there are different ways that these abstractions can behave in the context of transformations that affect duration and time and transposition and other things, loudness, that we'll see. So that's the big idea. A behavioral abstraction is a sound event that can behave differently according to the context in which it is instantiated. So we're going to see how this actually plays out in Nyquist now. So first of all, the idea of behavioral abstraction is an extension to the ordinary semantics of languages like Lisp or SAL or Python or C. We have behaviors, we have an evaluation environment, we have transformations, and we have temporal combinations like using sequence and sim or simultaneous. So, as I said, a Nyquist sound expression denotes a whole class of behaviors, A specific sound is computed by the expression and depends upon the environment. So what's the environment? Well, the environment contains information about transformations like stretch and transpose that can alter behaviors. And again, in contrast to something very simple and naive like a linear transformation, a behavior can do anything. When you play a longer note, you don't want to simply stretch the signal. And so this behavior concept is really critical for music. Let's get back to the environment. So to implement this concept of behaviors, all Nyquist expressions evaluate within this thing called an environment. And the environment includes the starting time, a stretch factor, transposition, a legato factor, a loudness, sample rates, and some more information. And this information is available to expressions, but the environment is in some sense hidden. You don't, there are actually ways to get at some variables that tell you what's in the environment, but I would like you to think of the environment as hidden, and you can only modify the environment through special function-like constructs that we will take a look at. So, first example, going back to sine tone created by the OSC unit generator, we can stretch that using the tilde operator and a stretch factor. So within the scope of this tilde, within the stretch, all the expressions see an altered environment with a stretch factor of 3, and they behave accordingly. Scoping is dynamic, which means the scoping of the environment is dynamic. So if I define a function called tone that returns OSC of C4, and rather than stretching OSC directly, I apply the tilde operator to tone, this environment created by the tilde operator to stretch by 3 is inherited by anything that is called directly by tone and indirectly by tone. So the OSC inside of tone gets the stretch. Transformations can also be nested. So the stretch operator applies to the environment, and there can be further applications of stretch to the environment. So in this last example, tone returns OSC stretch by 2, which nominally would mean a 2-second long sine tone. But if I then take that and stretch by 3, I get a duration of 6. The 3 multiplies by the 2. You can override the inherited environment by using special operators. The absolute stretch operator is 2 tildes. And so, for example, if I say tone 2 returns OSC absolutely stretched to 2, what that means is the environment seen by OSC is going to have a stretch factor of 2 no matter what. So if I play tone 2 and apply a stretch factor of 100, or even an absolute stretch factor of 100, that will be overridden inside of tone 2, and the value returned will always be a 2-second tone. Now, why would you do something like that? Well, think about this musically. Suppose you want to represent the concept of, let's say, a drum stroke, okay? It's something that if I write a quarter note for a drummer, what's the drummer do? Makes a drum sound. If I write a half note for a drummer, what's the drummer do? Plays a drum stroke. If I write 5 whole notes tied together and tell the drummer to play it, what does he play? Right? Okay, so I need to have some abstraction such that when it is stretched, when the environment says stretch, the actual sound computed may not actually be stretched. It may be like a drum stroke. All right, now the other thing that might be confusing, probably all of this is a little confusing at this point, but one thing that hangs people up a lot is they don't get the difference between behaviors and sounds. Okay, and the difference is that a behavior, the idea of a behavior is it's something, basically a function, but an expression, something that you're going to compute. Okay, once you compute it, the result is a sound, and sounds are immutable in Nyquist. You cannot change, sounds do not change. If you apply a stretch operator to a sound, the sound does not change, it does not stretch. So the stretch is applied to the environment, and the environment is used by the unit generators, and the results of the unit generators is effectively frozen. It's immutable. So let's talk about this sound type that comes out of unit generators. Here's an expression, OSC C4 absolute stretch by 2. So when OSC is evaluated, it uses the environment, in particular the start time and the stretch factor, and it returns a sound. And we can see in this picture that the sound that's returned has a start time, it has the sound itself, the signal. The signal is represented at some sample rate. The signal has the sound has a logical stop time and also a terminate time. In this case, in the case of OSC, these are both the same, and it's simply when does the signal end. But it's important to know that signals have endings. So all of this information, the samples of the signal and some extra information like the start time, stop time, sample rate, all of that is part of a sound. Here's an example. We're going to say begin with, remember, create a local variable x equals OSC C4. So we evaluate OSC C4, we get a sound from that, we assign the sound to x, and now we write play x stretch by 3. Now what does that do? That is going to produce, is it a 1 second sound or a 3 second sound? Okay, the answer is a 1 second sound, because that sound assigned to x is now immutable, and the stretch factor is, we're evaluating x, the sound, in the context of stretch by 3. But the sound is already computed, it's already frozen, it's immutable. The next example, we are changing x into a function. We say function x, return OSC C4, and now we say play function call x stretch by 3. So what happens now is the 3 modifies the environment. The function call x is evaluated in this environment. The environment is dynamically scoped, it's inherited into the function call, and OSC of C4 is computed in that context of a stretch factor of 3. Therefore, it produces a 3 second tone that is returned by the expression, and that's what we play. We have lots of transformations in Nyquist. We've been talking about stretch and stretch abs. These are actually available in a functional form. You can write the word stretch, open parenthesis, how much to stretch by, and then write an expression. Or you can use these infix operators. Similarly, time shifting is done by the at transformation, and there's an at abs, and we represent those appropriately by the at sign. Other transformations don't have special operators. We just don't have that many special characters. This is not APL, if you've ever taken a look at that language. So we use symbols like loud, sustain, and those are other transformations. We also have a special form that sort of undoes the environment. It's called abs-env. So that's an absolute transformation that puts everything at the default value. You look up other transformations in the manual, and maybe we'll talk about time-varying transformations later in the semester, but this is a very interesting idea that things like loudness and sustain can vary over time. And even more bizarrely, I think, the stretch factor doesn't have to be a constant, a scalar number. You can actually stretch by a signal and get a time-varying stretch factor. In practice, the most critical transformations are at and stretch. Those control when sounds are computed and how long they are. After developing all of this technology, I'm not a really big fan of extensive use of transformations. I think sometimes just explicit parameter passing is less confusing, easier to manage in programs. But at and stretch are just really indispensable. Also, technically, transformations are not functions because they do not evaluate their arguments in the normal order. Instead, they manipulate the environment, then they evaluate the behavior, which is an expression, and then they restore the environment. These are actually implemented as macros in XLisp if you're interested. And I think that should be clear. If I say OSC stretch by 3, if I go off and evaluate OSC and get a sound, and then evaluate 3 and get 3, and then try to apply some functions to them, then this whole behavioral abstraction business is not going to work. So these transformations are not normal evaluation order functions.